Okay, ladies, gentlemen, we continue. It's a very hot day, but I hope we will survive until 4 o'clock in this room and still have fun with mathematics. What I wanted to say first on the organizational side is that I uploaded a slightly improved version of the script. It in particular contains now the right way to depict the images. Yeah, so the variable names should now be better displayed in the graphs. And also I added a little section that I will present now, which I think is important, and I forgot to include that before. It's actually an addition to section 3.3. So I jump like a few pages back, and I want to actually rehearse and then start something new. So we are now back at 3.3, which was second order conditions. And you remember in these second order conditions, we learned a lot of new concepts which I would like to repeat with you now so that we are aware of them. So there was in particular this KKT matrix. So this was the second derivative of the Lagrangian with respect to the primal variables, and then there were these derivatives of all the active constraints that we called G tilde, and the transpose of that G tilde dW transpose 0. So this was an important matrix that we call the KKT matrix, and this matrix is basically invertible at a point where these second order conditions hold. Yeah? You remember we cited a theorem that if LICQ holds, it means that the rows of this are independent, and then the positive definiteness of the reduced Hessian, which was actually the Z transpose second derivative of the Lagrangian times Z, where Z is a null space basis of this constraint Jacobian. Yeah? So these are complicated objects. We introduced them all at the last lecture, but these objects are important things. So to remember the names, KKT matrix for this whole thing, and this was the reduced Hessian, and if the reduced Hessian is positive definite and LICQ holds, then we have these second order conditions, and then we had this wonderful result that we are stable against perturbations. So if we change the problem data a bit, the solution will not change drastically, which is a very important property for everything that you want to do in practice in numerics, because otherwise one could argue, yeah, you change a bit the discretization of some differential equation and you get to something completely different. There was one thing that directly follows from our stability under perturbations result, which I did want to present to you. And for this I need to repeat what was the result that we cited. So we said that minimizing a function f of w, which is our problem, that could be perturbed by adding some small scale vector that I call delta f to the objective, which basically tilts the objective a bit. And we could also perturb the constraints by adding some quantities to the equalities and to the inequalities. This is for the equalities, and likewise for the inequalities. Yeah? And then we could actually summarize these two things in a vector, and maybe I should directly say we then decided that we would anyway regard those inequalities that are active as an addition to this G. So that's a new notation that we discussed. So I will directly look at this point now. Under strict complementarity, this is a solid and nice way to state everything. So we have now a problem that is perturbed in a parameter delta that depends on delta f and delta g tilde, the two components. It's all together in a high dimensional space, of course. But when we change delta, we will get different solutions. Yeah? And these solutions we call W star of delta and lambda tilde star of delta. Yeah? So you see that this is, if you would change your problem a bit by these strong perturbations like adding something or adding something to the gradient, you will change the solution. And then there was this result that I will now just cite, that in fact it is this matrix inverse that tells you how your solution depends on the data delta. So what we got is that this dw star, this vector of w star and lambda tilde star together, if you differentiate that with respect to all the deltas, then this derivative is given by the negative of the KKT matrix to the -1. So exactly this matrix. And because this matrix is invertible, this is not infinite. And that's the main message here. And the theorem can be proven based on the implicit function theorem. But now I want to make one conclusion from this theorem, which is maybe giving a very nice view on the multipliers, but also there's two results which immediately follow from this. So the question we could ask is how would the objective change? So how does f of w star of delta behave locally? So when we change these data, we make errors. These errors will somehow influence the solution, and then we could plug in the solution, at least the primal variable of the solution, into the objective function itself to see if that changes the value of the objective or not. And now the interesting thing is the following. I give a headline to this. The headline is multipliers as shadow cost, or as shadow prices. That's the headline we give it in the script. And what we can do is, the idea to answer this question is that we just look at Taylor series, right? So let's just differentiate that function with respect to delta and see if it changes. So does the objective get better or worse if we change this delta? So what we do is we differentiate this whole thing. So the total derivative of this expression here with respect to delta. And obviously this is nothing else than the gradient of f with respect to w transpose times dw star differentiated with respect to delta, which is the upper part of that. So we can also write it using that result as just saying, okay, what we have is nabla f, the gradient of the objective with respect to its variable, and here we have zeros, and we multiply this vector with minus, I put the minus to the front, with this KKT matrix. So this would be the derivative of this whole objective with respect to the perturbation, so the KKT matrix. Okay, so this looks like, okay, a useless expression. We can, of course, compute it if we have the numbers, but is there maybe some more meaning that we can give to it? And the interesting fact is that this can be computed explicitly at the solution, of course. This is all at delta equals 0. Yeah? So we should evaluate all these functions at the corresponding solution. And the interesting result is that this whole thing here is given by the following vector. It's a vector that is decomposed into two parts. I mean, one part corresponds to the first, the perturbation in the objective, the other part to the perturbation in the constraints. And the surprising result is that there will be a zero here, a zero vector. That means no dependence on the perturbation of the gradient. And here will be a lambda tilde star. So the multipliers tell you how much the objective value would change if you change the delta here. So this looks like too simple to be true, right? But this can be easily proven, and I will just do it. The proof is that if you have at the solution what do we have? At the solution we have a nabla f. I omit the argument, it's always at the solution, right? So nabla f times dg tilde dw transpose times lambda tilde star. So that's 0, because our Lagrange gradient is 0, right? So now we could look at, what is this inverse here? It's just the solution of the following linear system. We need to have the gradient here. And then we have the KKT matrix here, which I write in a few more details to make it clear, d tilde dw, and here we have the second derivative of the Lagrangian, 0. And that should be multiplied with the two components of the unknown that we look for. Maybe I call it, how should I call it? Maybe I call it d, it's this derivative, huh? So, but I give them just some names. But they should be related, yeah, so maybe a gradient in W direction and the gradient in G is not good, right? Maybe dW and dG, because this is like the disturbance in these directions. So this is the equation system that just we need to solve in order to get the solution of this linear system. You agree? Okay, and so these two components, what I want to show is now very easy. dW equals 0 and dG equals lambda tilde star. We can check if that is a solution. And it is a solution. Why? Because if we put in a 0 here and a lambda here, then we get actually nothing from this column. Yeah? The lambda here will be multiplied with that. Together with this, it will give this expression, which equals 0. And at the lower part, we have only zeros anyway. So this is a solution. Well, that's easy to see. But because this matrix is invertible, it is also the unique solution. Which is the unique solution due to regularity of this KKT matrix. So if this matrix is invertible and we have found one solution to a linear system, then we have found the solution. And so in that sense, we don't really need to do MATLAB computations or whatever. We can just look at the solution properties and then we have the result. So that is already the proof of this little statement. But what does it mean? So there are two consequences from it, and both are really, I think, interesting and important for practitioners of control. And so the first one is extremely easy to see. I mean, if you change somehow the gradient of your objective, it will not change the optimality of your result. It's very surprising, isn't it? I mean, you solve a wrong problem. You have actually a slightly tilted problem. Yeah? So you will actually finitely, you will really have a different solution. But up to first order, it doesn't change your result. And that's actually due to the fact that, no sensitivity, I call it sensitivity, right, of the objective with respect to objective gradient errors. Yeah? I mean, it's already, maybe I should say, of course, if there's an absolute value, it would not change the solution at all. So that's why we added already a gradient to really have an effect. But still, even though we added already a gradient that, so to say, pushes your minimum to some other place, the resulting objective, if you plug this solution, this wrong solution, into the right objective, will not be perturbed a lot. So this is something that I sometimes call the robustness against wrong implementation, which is also a consequence of that. And what I mean by that is if you optimize something and you say, oh, the optimal length of some cable in airborne wind energy, for example, is 525 meters. Yeah? And then someone says, yeah, but it's much easier for us to just have a 500 meter long cable. And then you say, okay, it's not the optimal result, so you shouldn't do that, right? But then if you look at the following, that if you optimize over a variable, you will find the optimum somewhere where the variable is actually making, where the gradient with respect to exactly that variable is 0. And so due to this fact, when you implement it slightly longer or slightly shorter, it will not change, at least not to first order, the value of your objective. Yeah? And so the same happens when you implement now, due to these perturbations, it will actually push your solution higher or lower. It will really change your solution, but up to first order, it will not have an effect due to this fact. And that also holds in the presence of constraints, because all the perturbations that you can induce by tilting the gradient, they will still remain in the feasible directions. Yeah? So orthogonal to the feasible directions, a gradient has no effect. And parallel to the feasible directions, the gradient will actually only perturb a situation which is anyway flat in the direction in which you perturb. So that for that reason is sort of something robust against objective gradient errors. So that's the first thing. So this 0 here at the beginning has a particular meaning, which is very easy to see actually if you have a completely unconstrained problem. Yeah? If you have a completely unconstrained problem, this picture would be exactly the right picture. So tilting your objective a bit will actually move the solution to the left or to the right a bit, but because the solution is the minimum, it will not change the objective to first order. Because it will always be a bit worse to not implement the optimal value, but it's not a lot. Yeah, it's up to first order, it's nothing. Okay, so the first message is this, and the second message is what I call these shadow prices, or it's this. So if you have a constraint and you replace it, I mean, let's write it in detail. We had this G of W plus delta G equals 0, and we had the other perturbation, which was delta H of W, delta H, that should be smaller than 0. So these two things together, and of course we notice that the inactive constraints will have no effect, and that's why we added this G tilde, which was G plus sum of the HI, where the I is the active constraints, right? So that was the setup. But what does it mean now? If we say that the objective, if you change your constraints, how does the objective change in the solution? And that means that if you make your delta bigger here, that your objective function will be also becoming bigger. That means worse. Yeah? And if this derivative turns out, if the Lagrange multiplier is, I forgot to say that it depends on the sign of the multipliers, right? So if a multiplier, yeah, a multiplier lambda I or mu I at the solution, of course, is positive, a positive perturbation, of course the corresponding ones, a positive perturbation delta Gi or delta Hi will increase the objective. So perturbing the problem will cost you something. And likewise, of course, if you would reduce it, a negative perturbation would decrease the objective. And so it's the product of these two things, right, which matters. Maybe to just write it explicitly, I would just say the derivative of f w star delta, the delta times a perturbation or times a delta is of course nothing else than just dg tilde, lambda tilde star times delta. Delta g tilde, it's only the constraints, which is then actually the same as lambda. I think this is the right way to express it. It's the sum of 1 up to n g of lambda star I dg I plus the sum of all the mu's I from 1 n h times d h I. And now interestingly, because the inactive multipliers are 0, I can even count over all. Yeah? So they are having the multiplier 0, so they don't have any cost. So it doesn't even matter. So this is the main formula here. Maybe this is the result. So if you perturb your problem with a delta in this form, then the objective will increase or decrease according to these products. And so there are two remarks or two notes. Yeah? So first note. The first note is that for inequalities, this really makes complete sense. So what happens if we increase a delta here? It means that we make it more difficult to satisfy this constraint. Yeah? Because we add something to something that should be smaller than 0. So if we add something here, we make from a big feasible set, let's say this was the feasible set before, yeah? So this is the region where h is smaller than 0. And after we add this delta, we make it a smaller feasible set. Yeah, it could look like this. But we definitely make it more difficult, so there's less points. We tighten the feasible set. So if we increase the delta, we make the feasible set smaller. That means that the objective can only become worse. And that's what this multiplier says. So the multiplier mu I is positive. We said that before. They are always positive. So if you increase some of the inequality constraints by a delta, you multiply the delta with a positive multiplier, and you see it's always getting to be a worse objective than before. So implicitly, you directly see that it would never make sense to have an inequality multiplier that is negative, because then it would mean that if you tighten the constraints, you get a better objective, which cannot happen. So, so inequalities are positive. The multipliers must be positive. I mean, we said that before, but here's another for this to make sense. And they are. In the KKT conditions, they are positive. There's a second note that is corresponding to the fact that we, anyway, in the Lagrangian, I said at some point yesterday, on Monday, you will have the units of multipliers must be objective divided by constraint. That's the unit of a multiplier. So that also comes back in this formula here. So if you, this whole object, I mean the derivative of the objective in the direction of perturbation is, if you multiply it with the perturbation, this has the unit of the objective. Let's say euro. Yeah? The perturbation, if this is, for example, a constraint in meter, yeah, then this perturbation will be also, I make it like I say, my surface area, or no, sorry, my length of something should be 1 meter longer. So I give something in meter. Then I have, I want to get euro, and I have meter. So then this unit of the multiplier must be euro per meter. And that's exactly what it is. It's the cost of a constraint. It's how many euro does each meter that I ask for cost me. So it has a real meaning, a sensitivity of the objective with respect to some constraints. So the second node, 2, is units match. The unit of lambda, I, is the unit of f divided by the unit of g. GI. Each constraint has a different meaning. So cost per unit of constraint. Yeah, that's of course a funny thing. But it has a very visual meaning. So imagine that you are an optimization engineer sitting in a company and you say, and your boss comes to you and says, I think we could easily build a kite with 500-meter length. Yeah? So now it's a constraint. So you add that to your optimization problem and you say, we can optimize, but of course the length is now restricted to have 500 meters of some cable or whatever. And then, yeah, the solution is not so good. Yeah? You tell her the result is this, and then your boss asks, so maybe what would happen if we change and we buy this cable from another company and it can be longer than 500 meter, for example. Yeah, and then you say, per meter we should gain so and so much, and that's exactly what the multiplier will tell you. Yeah? So the multiplier has a very intuitive meaning, and we will come back to this meaning of the multipliers in the context of optimal control, because these multipliers will be extremely, or some of the multipliers will have a, I think, very beautiful relation with the gradient of the cost to go function, which is just something we will learn after knowing dynamic programming. Okay, so that's why I wanted to add this, and also because it's a very useful optimization knowledge. So the summary is, if you perturb a problem, you will get, of course, a different solution. But how much does it matter in terms of objective? If you change the gradient, it doesn't change the objective up to first order, and if you change the constraints, it will change the objective in a way that's proportional to the constraints. So roughly speaking, if you have constraints and they all are with the same units, then you can compare which of the constraints is more binding than another one. So to say, if it has a higher multiplier, you see this is really an expensive constraint. And another constraint with a very small multiplier, and if they have the same units, you could say this is less expensive. Okay, so this is one important practical thing on the theory side. Are there still questions regarding chapter 3? If not, then we jump back into chapter 4. Where we are already, and I will continue with chapter 4. Also by a short rehearsal, what do we do in chapter 4 at the moment? So we regarded just one setup, namely the optimization problem with equality constraints only, and we derived an iteration which would actually go as follows. We would just say we iterate in a primal dual space, and the new iterate wk plus 1 and the new lambda k plus 1 would be given by, and now the interesting thing was that it's an the old iterate. We don't care about the multipliers because of some magic reformulation that I mentioned. And we have here the KKT matrix, inverse. So I put only the 0, then you know it's the KKT matrix, maybe. Yeah? Maybe I put it in more detail because we said that we could approximate the Hessian, and here we have the correct, we call it G only, the correct Jacobian, and we multiply this with nabla F, the objective at the last iterate, and the constraints at the last iterate. So note the slight reformulations that we used. So here is no lambda k, and here is no gradient of the Lagrangian. Yeah, so the alternative, and we proved that it's the same, so this could be equivalently written like this, the gradient of the Lagrangian. Yeah, so everything the same, and the matrix is the same. But by a little trick, we moved this away so that here is a 0. We could actually, in particular, we need only the gradient of the objective here. And for example, By the way, interestingly, this is related to what we just proved there. If you happen to be at the solution, right, then you know already that this G is 0 anyway. But let's say you know the primal solution, then you could build all these things. And then you see that after, because you're at the solution, the next step will be at the same solution and the multipliers will be coming out of this formula. So it's the same formula that was used here for the proof. So we can now replace here, as I said, the Lagrange gradient with the objective gradient, and then we have a slightly easier way to compute everything. Usually keep the constraint Jacobians, so these things constant, correct, exact. So that's what we do, and we only approximate the Hessian. That's not necessarily always the case, but mostly. The Hessian of the Lagrangian needs to be approximated, and we said that BK should be somehow similar to the Hessian of the Lagrangian at the current iterate. The Hessian of the Lagrangian with respect to the primal variables, of course. And so then we derived one method that we could call exact Newton. Exact Newton is clear. It's everything the same. This was the first method we already introduced, and the second one was that we call the Gauss-Newton, or the generalized Gauss-Newton method. Generalized Gauss-Newton. And what did we do there? We chose this particular Hessian, but a Hessian that we can only choose if we have an objective of a quadratic form. So I should say only for f of w being 1/2 of the norm of some big F of w. So only then it can be applied. And there we choose BK to be df by dw at wk transpose df by dw wk. And we derived that this would be something like the leading term of the true Hessian. So this is maybe a remark. This would be second or a quadratic convergence. And this was linear convergence. Okay, so these are the two ways to approximate the Hessian that we had introduced already, and I want to go on by introducing a third one, which is also quite popular, and which I think you should know about because it is used. And this is quasi-Newton updates. So maybe I should first come back to the general form here. If you look at this general iteration here, you need to know the gradient anyway, and you need to know the derivative of all the constraints. And it's not very strange to see that you need them, because you need them even to check if the gradient of the Lagrangian is 0, which is the optimality condition. So without evaluating these derivatives and these derivatives, and of course the value g, you cannot even check if you are at an optimal point. So you expect that this is something you have to evaluate in each iteration anyway. But the second derivative of the Lagrangian, that can be very costly. And so that's why this exact Newton method has some disadvantage. It has expensive derivatives here. And also, what we compute here could be expensive, and then it's also leading only to linear convergence. So the idea of quasi-Newton methods is could we somehow approximate this BK by something that's maybe starting with a unit matrix, make it better and better, building on information that we have anyway, namely on the derivatives of these two things only, which we compute in every iteration. Yeah. So the idea is successively build better approximations, better Hessians, or Hessian approximations, by doing something like bk plus 1 is something that depends as a function, maybe I call it phi, of the old bk. Of course, if I had already a Hessian, maybe it's a good idea to stick to it, but also of two things that I will define in a minute, sk and yk, where sk and yk are actually the steps that I do in the Lagrange gradient and in the primal variables. Yeah? So I define it first and then I explain why I use that. And sk is actually wk plus 1 minus wk. So after I have done this whole step, I know both wk plus 1 and wk. So I can define this thing, and for the next Hessian I could use it. And I also define yk, and this is now the gradient, the Lagrange gradient difference. So it's the Lagrange gradient at wk plus 1 at the latest multipliers that I have. It's the gradient with respect to w. And the Lagrange gradient at the past point wk. And maybe I should write down what this is in detail. It's of course the objective gradients, yeah? But it also depends on the constraint Jacobians at the point k plus 1 and also at the point k. So I need to store the old objective gradient, the old constraint Jacobian, in order to be able to evaluate this thing. And afterwards I can throw them away. I will not detail that. But the main message is this is all information that I need to anyway compute per iteration. Here I already use the new gradient and the new constraint Jacobian, which I will need in the next iteration anyway. Yeah? The next iteration I need this thing at k plus 1, and I will also need the bk plus 1. So it's all in line. There's no extra computation, no extra derivative at all. And maybe I should explain why do we use these two things, and maybe I should maybe state the requiring the secant condition. We require a condition here, and this condition that we require is that the new Hessian bk plus 1 times sk should be equal to yk. And that really makes sense, and I want to discuss with you in a minute why this makes sense. What we want to approximate is the second derivative of the Lagrangian in the direction w. What we have available is the difference of two gradients of the Lagrangian. So that's actually and what we have available is a step in the variables w. So if you think of finite differences for derivatives, if you divide, so to say, this difference by the step, then you would get this an approximation by finite differences to the second derivative, right? But of course, it's a metric, so you cannot divide by s. So otherwise, I would write the s here, right? So the best thing I can require is that if I evaluate my derivative, which is this b, I mean, my derivative of that function is the second derivative, right? So if I evaluate my derivative in the direction sk, then it should give me this change. So that's what I would expect a second derivative to do. And so this is a condition that I can require and which is non-unique, because I mean I have n equations if the variable space has n dimensions, but this new matrix has n square half, because it's a metric, n square half entries. So many more entries than I have conditions here, and so the remaining conditions or the remaining degrees of freedom are just a true choice, and there are different choices, and that's why there exist different quasi-Newton updates. And the most popular one is one formula, most popular and I think also most widely used, and in most cases also a very successful formula is actually the one that says bk plus 1 is equal to the old bk, and then come two modifications of rank 2, and I cite this formula to make no error. So most popular is the BFGS formula. It stands for Breuden, Fletcher, Goldfarb, and Shanow, which were people that independently discovered the same formula in nearly the same years. And you use here, I will first write it down, SK transpose BK SK, and then plus, and here it's YK transpose divided by SK transpose YK. So this is a formula that leads obviously to a symmetric matrix. Yeah? So think of it, what we have here and here. This is a standing vector, that's a lying vector. Here again a standing vector and a lying vector. So together they are dyadic products. Yeah? So they are rank 1 matrices. This is a rank 1 matrix and this is a rank 1 matrix. And they are added to the old matrix. But the other thing that we can very easily check, and just check it if you like. So you can compute this, and you can just realize that briefly, if I put the SK here, then this thing will end with YK, this thing will end with BK times SK, which is then subtracted with this and gives 0. So we can indeed satisfy the second condition, but that's not a big achievement. The main point is it has nice other properties which make it very useful, and that's why it's widely used. So what this method does, it will just update the matrices all the time, and what you will get is superlinear convergence. So in principle it gets faster and faster. Sorry, I will switch off the mobile. Okay. And the reason why it's superlinear is because these matrices BK, they get more and more similar to the true Hessian in the directions in which that is needed, namely in the free directions of your which are free due to the constraints. In the other directions, it doesn't matter if your Hessian is correct. Good. So now you know a third method for approximating your Hessian. And I think it's a good idea to stop here and to have a short break of 10 minutes, and we continue 10 past 3. Okay, are you ready to continue? I'm sorry for being a few minutes late again. I want to conclude with a few detailed discussion points on local convergence of Newton-type optimization methods. And also here I want to add a special thing that is not yet in the script, but which will be there hopefully by the end of the week. So it's 4.2, local convergence of Newton-type optimization. And it's all completely following what we did before, so I don't need to repeat much of it. But the only things I want to say is that we had our function r of z, which was given by the gradient of the Lagrangian and g. We had our true Jacobian of this whole thing that was playing a role in the Newton-type methods, you remember, which is actually dr by dz, which in this context was the second derivative of the Lagrangian, the dg by dw, and the dg by dW transpose and the 0. So that was actually the exact KKT matrix. And then we had the iteration matrices MK that were given by the approximations, which were now BK, and here we have dG by dW and dG by dW transpose with a 0. And then the iteration was nothing else than zk plus 1 is equal to zk minus mk to the minus 1 times r of zk. And then for this one, we know already this local contraction theorem with the omega and with the kappa, and we know that these things very much depend on the difference between the j and the m. And so I want to just compute the terms that are necessary, and the main term is j, zk, no, actually mk minus j zk. Yeah. What is this? It is a matrix which, due to the fact that we choose the constraint Jacobians to be equal, this matrix will only be having non-zero entries at the upper left corner. And here we will have bk minus the second derivative of the Lagrangian at wk and lambda k. Yeah, so this is, maybe put the w here to make sure that it's all only with respect to the variable w. So it's the difference between the Hessian and the Hessian approximation that really determines about the convergence speed, and that's why Isaac Newton, as I said already, has quadratic convergence. At Gauss-Newton there will be a persisting error here, hopefully small, but it has linear convergence if it converges, and this BFGS method makes these matrices similar enough that it will actually lead to superlinear convergence. Yeah, everything is a corollary to chapter 2. Yeah, corollary to theorem chapter 2. So I will not repeat it, and I think I will also shorten the current version of the script. But what I want to add, and which I want to extend here, is something that is like a tight condition for local convergence. And maybe before I continue, I just want to make sure that you find it all rings bells what I write here, because I didn't write a new theorem or anything, because it's basically an application of our old theorem. Is there some desire to clarify these things more? No. You can also say yes. Then I can try, or you can ask questions if you feel like. Mm-hmm. Okay. Then I will continue by stating something that is a bit less standard, but about which I thought for a while, and where we have a simple and nice solution. So this is, I mean, the similarity of these matrices, you remember, were a sufficient condition for local convergence. Now, the question is if we have a tight condition for local convergence. And you remember for the general Newton type case, we had a tight condition that was just the assumption was that m is a function of z, right? And then you remember with this we could somehow say, oh, let's just look at the difference between 1 minus, and then I think we had m at the solution to the minus 1 times j at the solution to minus 1, and this matrix, if it had all the eigenvalues in the unit circle, then it was a contracting map, and otherwise not. So rho smaller than 0. This was what we, smaller than 1. This was a tight condition for local convergence. And so now it's a bit more involved, or it's not more involved, but the matrices are more complicated. So the question is, what does it really mean in the context of where we only approximate the Hessian matrix? Yeah. So the assumption here is only that bk is given by B of WK. And maybe even lambda k. So it's just a function of our variables. Yeah? So C1 function to be on the safe side. Okay, so it's just an example for this would be Gauss-Newton. GGN, generalized Gauss-Newton, that has this form. There are many other algorithms that could be brought into this form. So your Hessian approximation is something that depends only on your data. BFGS is not of this form. Exact Newton is of this form. Gauss-Newton is of this form, but updates are not. But if I have this assumption, then I can actually state the following, and this is maybe the theorem that I would like to prove, but I will not prove it here, but I will prove it in the script then. So with the definitions that we had before, we can just state the following. This thing is smaller than alpha, which is smaller than 1. Yeah. For some alpha. Yeah. For any alpha in the interval from 0 to 1. This condition is equivalent, and now it's a bit funny what we have, but it will be equivalent to a condition on the Hessian matrix only. And I will write down the condition and afterwards explain it. So it's a condition on the Hessian at the solution. Yeah, maybe I should call it B of zk, right? Because z is all the primal and dual variables. And it turns out that this Hessian should be neither too big nor too small. So it should be upper bounded and lower bounded by some things which have a relation to the true Hessian. And I think I need more space, so I will put it here. I will develop it step by step, but I need more space. So it should be smaller and bigger than something. And it turns out that it should be smaller and bigger than the exact Hessian of the Lagrangian at, maybe I also write Z star for the combination of primal and dual variables. So it will be upper and lower bounded by the Z star, by the exact Hessian. If I would just leave this statement, it would just mean it must be equal, right? So there is no gap, right? Then it should be the same. This is certainly not the case. And there will be two modifications to this thing. So the first thing is that we only will need this Hessian to be somehow similar on the null space of the active constraints, which I need to define, but which we remember very often we express with big Z. So I will put a big Z here, on the left and on the right, everywhere. Yeah, so there's a big Z, the big Z here, the big Z here. So I need to project it, that's the reduced Hessian. So now is something I'm only concerned about the reduced Hessian, because in the other directions my Hessian will not matter. So still this is not giving any freedom in the reduced Hessian at least. So the freedom comes by dividing these things with factors that are positive and negative, I mean making it bigger. And the factor will be 1 minus alpha here and 1 plus alpha here. So if alpha is 0, then this is indeed the same as this, right? Because then it's just divided by 1. And that means I get a contraction with infinitely fast rate, which is basically what I have in Newton's method, only if I have the right Hessian, right? But now, if I still want to get convergence, I need to have some contraction which is at least a little bit smaller than 1. So what happens if I put 1 here? Yeah, so maybe extreme cases. I put 2 extreme cases first. I will not prove it here, but I will discuss it. So, no, maybe first I need 2 definitions. Definition Z is a null space basis, null space basis for dg dw at w star, as before. Z star is of course a solution, and yeah, I think there's no other definition necessary. But I have extreme case 1. Alpha equals 0. That's what you would have for Newton or quadratic convergence. I mean, it's where this contraction radius is 0. I mean, where you contract with a rate which gets fast, extremely fast, namely quadratically. There we would have actually, the meaning is that the reduced Hessian equals or equal to exact one, exact reduced one. So, sorry, the reduced Hessian approximation approx is equal to the exact reduced Hessian. So what we would have here is that we just have the equality. Basically, we could also state it in different forms. I mean, one form would be that I just say Z transpose multiplied with the difference between our Hessian approximation with the true Hessian at the solution point. This should be equal to 0. So that's a translation of the statement with the two matrix inequalities here. But if there's the same on the left and on the right, it basically means this should be 0, right? The difference should vanish in the null space. The other case is a bit more funny, extreme case 2, alpha equals 1. Yeah, alpha equals 1 means that it's just not converging anymore, because it's not contracting with linear rate. It's just marginally stable, so to say, the Newton method. But what would it mean? It would just mean that this inequality you divide by alpha, 1 minus alpha. Alpha is now nearly 1, yeah? Or it is 1, so you divide by infinity, so you have no upper bound. It can be arbitrarily large. But on the lower bound you have something that it should be 1 plus alpha is 2, actually. So you see that the only remaining bound for alpha equal 1 is actually, how do I express it in the most elegant way? I think this is the best way. I say Z transpose, and here I have my B Z star minus, and here I subtract from it half the Lagrangian Hessian, and I restrict it on the null space again. I mean, I can either first form the reduced Hessians or bring it into this form now, and this whole matrix should be positive definite. So roughly speaking, I mean, this has a meaning. Roughly speaking, your Hessian approximation must be bigger than half the true Hessian, at least in the relevant directions. I mean, it's always the reduced Hessian that only matters. The reduced Hessian must be bigger than, sorry, I always forget approximation, because the Hessian approximation must be bigger than 1/2 the true reduced Hessian. And that's interesting because it allows you to devise methods, and you could just in your experiments, when you're really, really lazy, and in some of our examples we will be very lazy. We don't want to compute a Hessian, and we don't want to do Gauss-Newton or Isaac-Newton or BFGS. We just say a factor times a unit matrix. And this statement says if this factor is big enough, then you are bigger than half the true Hessian, in all directions, in all relevant directions, then you should be fine, at least for local convergence. And that's the motivation why very often people choose high Hessians in optimization. It will just make their algorithm slow. Why will it make it slow? The rate alpha that you can achieve is not very high. I mean, you're very far away from the true Hessian, but still there is alpha can be 0.99, and then you divide here by 100, and then you have enough room. So, so the consequence is of this thing: choose Hessian high enough to be on the size on the safe side. To be on the safe side. I think I want to give you an example for this, because otherwise it's a bit useless, right? An example, I will choose a constant Hessian. Hessian approximation. B, and I will only regard the unconstrained case. So then we don't have these null space and so on. And so then our iteration is actually this one. It's just, unconstrained also means Z is equal to W, because there is no multipliers. And the iteration then will be WK plus 1 is equal to WK minus B to the minus 1 times nabla F of WK. So that was the simplest case of a Newton method. And now I choose even F from R to R, just a scalar example. And I choose some F that I find nice, which could be, for example, what should we take? Something slightly non-trivial maybe. No, I even choose a trivial one, because then we can even easier see what I mean. So I choose a very trivial one, so I say F of W is equal to 1/2 W squared. Okay, very trivial. What is its gradient? Gradient will be just W. So now what is our iteration here? Our iteration is, I should also compute what is the second derivative of it. So the true Hessian. Now I could just look at what happens here. I mean, I now have an iteration matrix WK plus 1 is equal to WK minus B to the minus 1. B is now a number, by the way, times WK, right? So I can also see, okay, this is actually 1 minus B to the minus 1 times WK. And you see immediately when will this converge? It will converge if the spectral radius of this matrix is smaller than 1, which is actually the case if, and now we should check when will it converge? It converges if, this can be positive or negative. B is in this case just a positive number. So this inverse is also a positive number. If 1 minus B to the minus 1 is smaller then maybe I should converges with speed alpha. If this is smaller than alpha or bigger than minus alpha. You agree? Then it will contract. Of course, it could, in the case that it's negative, it would oscillate. In the case that it's positive, it will contract from the top. But anyway, so it will contract like this, duck, 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 to the solution, or it will contract like this, duck, 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 duck. But in both cases, it will contract. With the rate alpha, where this is, so to say, alpha to the k. This is k, the iteration index. Okay, so where does it translate to? So now I try to translate this thing into, I nearly get the theorem, so to say. What will I do? I will add I want to make conditions on the B only, right? So I get rid of the 1 by subtracting a 1. So I will get minus alpha minus 1 smaller than minus b to the minus 1 smaller than alpha minus 1, right? So that's okay. Now I get rid of the minus by inverting every sign here. Alpha plus 1 is bigger than b to the minus 1 is bigger than alpha minus 1. And now I get even rid of the sign because all these numbers are high. I didn't change that sign, right? So with alpha smaller than 1 or smaller than equal 1, now because all these numbers are positive, I can also invert it by taking the inverse, and now I get b. And now the signs change again, 1 minus 1 alpha, and here's 1 divided 1 plus alpha. Yeah. So now what I see is that, again, my condition is that the b should be bigger than 1/2 if I want to have convergence at all. I mean, with some rate alpha. Of course, it should be slightly bigger than 1/2, because if for 1/2 I would just get exactly a marginal convergence. So let me just check what happens if I do this iteration with b equal to 1/2, which is the limiting case. It's just half the true Hessian, right? So it's too low. It's at the boundary. What will be our iteration? Our iteration will be wk plus 1 equals to 1 minus, okay, b to the minus 1, which is 1/2 to the minus 1. It's actually 2, right? Times wk. So it means actually minus 1 times wk. And that's exactly the case where I oscillate without converging, yeah, unfortunately, around the solution. So if my Hessian is reaching this boundary, I will get convergence. Yeah? No convergence, sorry, I will just get oscillations. Do you see that? If I choose now the b a bit bigger, I will get this factor smaller, and then I will converge. So that's clear. But what happens if I choose my b ridiculously large, 10 to the 3, something really, really big? What will happen? So what will happen is that I have wk plus 1 is equal to 1 minus, okay, 10 to the, it's 10 to the 3 to the minus 1 times wk, which is now, of course, it's 1 minus 10 to the minus 3 times wk, which is actually 0.999 times wk. How does that look like? If this is the index k, iterations, and here's my starting point, then after one iteration I will have improved. It's of course difficult to plot it by a percent of a percent, or a tenth of a percent, and so roughly speaking it will converge. And I think I need 2 chalks and a bit of patience. So it will converge slowly, but it will eventually converge. Yeah? So it will be a converging sequence roughly. Okay, this is not a very nice plot, but it converges. Too high is still okay for local convergence. Too low at some point makes you oscillate, and if I make it even smaller, if this would be like a tenth, then it would just completely overshoot. There's a second interpretation which I just want to give you because it's nice and easy. There was this QP interpretation, you remember. So the QP interpretation was that wk plus 1 is the argument that minimizes a quadratic function, right? namely a quadratic function which had the gradient times w, and here the second derivative, w, wk, bk, w minus wk, and then here the constraints, g plus dg, dw, w minus wk equals 0. So you remember that interpretation. And of course, it's difficult to visualize it in the general case, so let's visualize it for the example. Yeah. For the example, what is the example? The example has an objective function and a variable. And this objective function, let me plot it this way. It has a nice positive curvature of 1, so that is f of w. And if I'm at some iteration, let's say here at this point, I will have a quadratic approximation of my problem where I have the correct gradient, but a wrong Hessian. So with my correct gradient, I will have the right tangent. But now I have some Hessian that could be either too big or too small. So for the case where I have b equal to 1/2, my Hessian will be something like this. So this is b equal to 1/2. And my minimizer of the quadratic problem will be just on the somewhere here on the other side. Yeah. If I have my Hessian b to the 10 to the power of 3, my gradient will still be correct, but now my quadratic approximation looks like this. So it's very highly curved. Maybe I put this in red. And the curve also in red. Yeah. And the other in green, even though it's not, I don't want to say that it's nice or something, just a different color. So this would be the approximation in green. And of course the perfect approximation would be the right Hessian, and then after one step I would have the solution, because this is such a trivial example. But this is maybe helping everyone to get a feeling of what a Hessian approximation and optimization means. Too high is usually not a problem, but makes your algorithm slow. And what you really want to have is that its approximation is correct, or close to be correct, and positive definite. Yes?
Just understanding. Isn't it all a root finding problem? So shouldn't be the y value or like the f of w value be the same for all of them? So it's 0. Yeah. Like, shouldn't be the red curve also go down to the bottom, and the green curve?
No. It's all correct. It's a root finding problem, right? But where the derivative of the function f should be set to 0, of course. Yeah? So you could plot if you want, and this is like the usual way to plot Newton type. If you want, I can plot the derivative of this whole thing. Then it would be in this, so I plot it here, right? So now I call the w, and for the unconstrained problem it's equal to z, right? And I can plot the derivative, which in this case turns out to be a very simple function, r of z, which is nabla f of w. So that is now the thing that you want to bring to 0. And what we do if we are at this point, so this was the point at which we are, then the red curve will give you a much too high derivative. And that's why it thinks here is the 0. Yeah? And the green curve will give you a much too low derivative, why it thinks that the solution is here. So here we are back in this picture of Newton's method. But the interpretation of a QP is also sometimes nice and useful, because it's all related to finding the minimum of a quadratic subproblem. Just a different perspective on the same fact. But the interesting thing in optimization is that, and also in Newton type methods, so to say, a too high derivative usually is okay. But too high for Newton type doesn't really make sense. I mean, it's a matrix. But for optimization, because we have these Hessian matrices and they must be positive definite in a solution, we can really say a too high Hessian is a good thing. Well, not necessarily good, but it's a thing that is not so dangerous. Okay. Yeah. This was new stuff, but I think, yeah, I thought it's useful to know about it because it really gives some practical intuition. I think, okay, not intuition, but it's a practical tuning rule. If you have an algorithm, in particular in embedded optimization, you might actually choose a fixed hessian, and then you would usually choose it slightly too big of what you think is the right one. Okay. I think there is no necessity to overcharge you today on this beautiful day. So what I suggest is that we stop here if there are no more questions. I thank you very much.